another minimal polynomial. Okay. Now, what are the immediate consequences? The immediate consequences are that the degree of this polynomial m star a of x must be same as the degree of the minimal polynomial m a of x. They must have the same degree. Why? Because if this degree is less than that, then you have a polynomial that has a smaller degree than the minimal polynomial that annihilates the matrix A. So this means MA of x is not a minimal polynomial, so it's a contradiction. But what if I assume that the degree of MA star of x is bigger than MA of x? That means now you have a polynomial of less degree, okay, than the minimal polynomial that annihilates the matrix A. So this means MA star of x is not a minimal polynomial. So there is no choice except saying that these two polynomials should have same degree. Okay, this is the one thing. The second outcome that I would like to say, we just proved actually that any polynomial that annihilates the matrix A must be divisible by MA of x, actually the minimal polynomial of A. Now M star A of x being a minimal polynomial annihilates the matrix A. So by this conclusion I can say that MA of x divides MA star of x actually. Okay? So that MA star of x is equal to some quotient of x times MA of x. Okay? Some quotient times of MA of x. In other words, MA of x divide M star A of x because M star annihilates the matrix A. You can think other way around as well. Okay? Now this is a strange statement. So imagine that the degree of this annihilating polynomial is 3, and so since both are equal, so this must be 3. The question is, what should be the degree of this polynomial? Okay, what should be the degree of this polynomial q of x? Now if the q of x has say degree 1, then this product is going to have degree 4. But we are saying that this product has degree 3, so it's a contradiction actually. So if this degree is 1, then that means that this polynomial has a degree 4, but it has degree 3 actually. Okay, so that would be a contradiction. How about if q of x is 2, you're still going to have the same contradiction. The only possibility in which you're not going to have a contradiction that this has a 0 degree. This has a 0 degree actually. Okay? In other words, since their degrees are equal, so the q of x must be a 0 degree polynomial. In other words, it must be a constant. It must be a constant actually. And if it is a constant, then that means that M star A of x must be C times of M A of x actually. Now what is M A star A of x? Say this is this actually. So this is A naught plus A1 x plus say AM x power m actually. Okay, no, this is going to be 1 third because the minimal polynomial is a monic polynomial. C times of, okay, C times of, this is also an m degree polynomial, so let's call it B naught plus B1x plus so on and so forth. What do you call x power m? Okay, x power m. Now if this is the case, then you're going to get CB naught plus CB1 x plus so on and so forth, Cx power m actually. Now if you compare the coefficients, these two polynomials are going to be equal if the these coefficients are equal, and hence this C must be equal to the 1 actually. Okay? Because this is a monic polynomial. They can't be, a constant other than 1 which can be the coefficient of this polynomial. So this C must be equal to 1 actually. This C must be equal to 1. And if the C is equal to 1, what does follows from this inequality? The inequality that follows from this equation is that these two polynomials they are precisely equal to each other. Okay? So this argument gives you, an interesting insight about the minimal polynomials. That minimal polynomial, so we know from the definition, it's the least degree annihilating polynomial of the matrix A. But this lemma tells you that if you have a minimal polynomial, it must be unique. Secondly, if you have any other annihilating polynomial, the minimal polynomial is going to always divide it. And we know by Cayley-Hamilton theorem that the characteristic polynomial is an annihilating polynomial for the matrix A. So this means that minimal polynomial must divide the characteristic polynomial actually. And let's see some of the consequences of it. Okay? Now I'm going to tell you that if you have been given a matrix, how to find its minimal polynomial. What is the strategy to find its minimal polynomial? Okay? And I'm going to spot to an interesting factor that you can have two matrices that has same characteristic polynomial and hence they have the same eigenvalues, but they can have the same minimal polynomial actually. So minimal polynomial is also kind of a canonical property of the matrix that differentiate the two matrices. So let's do two examples. Let's do this interesting example. Imagine I took a matrix 1, 1, 1, 4, okay, 0 to 1. I'm not going to do all calculation. I'm going to leave this for you, but I'm going to just mention the key things. 1, 1, 4, 0 to 0, and 0, 0, 2 actually. Okay? I know this is an upper triangular matrix. So yesterday we talked about it, that if you have an upper triangular matrix, its eigenvalues are the diagonal entries actually. Its eigenvalues are diagonal entries. So what are going to be the eigenvalues of this matrix? 1, 2, 2. And this is also an upper triangular matrix. What are the eigenvalues of this matrix? 1, 2, 2, and hence they have the characteristic polynomial. In other words, if you compute, say, the characteristic polynomial, then you need to compute the determinant of xi minus a. Actually, you can compute it, and it turns out that the characteristic polynomial of a is minus x minus 1 times x minus 2 square, which makes sense because this 2 is appearing 2 times on diagonal, so it should be, it should have 2 multiplicity. And if you compute, for example, the characteristic polynomial f the matrix B, you're going to get the same polynomial actually. Now, how to find, for example, the minimal polynomial of the matrix A? Okay? How to find the minimal polynomial of the matrix A? So first of all, you always start with the characteristic polynomial and see that what are the possible factors of the characteristic polynomial actually. So what are the possible factors of characteristic polynomial? So x minus 1 is one factor, x minus 2 is another factor, x minus 1 times x minus 2 is another factor, okay, and x minus 1 times x minus 2 square is another factor. So these are the possible factorizations of the minimal polynomial actually. Okay? So if these are the possible factorizations of the minimal polynomial, in other words, these are the polynomials which divides the characteristic polynomial. These are the possible divisors of the characteristic polynomials actually. Now that polynomial is going to be the minimal polynomial, okay, out of these divisors of the characteristic polynomial, which annihilates the matrix A, okay, which annihilates the matrix A. So if in this polynomial you substitute A and it turns out to be 0, then this is a minimal polynomial. If in this matrix, if you substitute A and turns out to be 0, then this is the minimal polynomial, okay, and so on and so forth actually. So let's compute, for example, if you take the first polynomial x minus 1 and compute A minus I, it turns out that this is not 0. If you compute B minus I, it turns out that this is not 0 as well. You can compute it easily. If you compute now A minus I times B minus I, A minus I minus A minus 2I, if you compute this matrix, it turns out that this matrix is equal to 0, 0, 1, 0, 0, 1, 0, 0, 0. So this shows this is also not 0. This is also not 0. So this means that the characteristic polynomial of MA of x is this, x minus 1, x minus 2 square. Okay? This is what the characteristic polynomial of the matrix A, because all other factors are not annihilating the matrix A. Okay? They are not annihilating the matrix A. So the annihilating polynomial of the smallest degree for the matrix A is this actually. Okay? How about B? You can check actually that if in this polynomial, if you substitute B minus I, this should be A minus 2I, yes. If we substitute B minus I, this is not 0. If you take x minus 2 and substitute B minus B in it, so the B minus 2I is also not 0. But if you take this polynomial, you always start the polynomials of the least degree. Okay? Always start with the polynomials of least degree. So if I move towards this polynomial, which is B minus I times B minus 2I, you can make a calculation that it turns out that this is a 0 matrix actually. Okay? So I'm going to say that for the B, okay, for matrix B, the minimal polynomial is x minus 1 times x minus 2. Okay? X minus 1 times x minus 2. So, what is the interesting conclusion that we got out of it? So, we saw two things. Number one, we saw that we have two matrices with the same characteristic polynomial but different minimal polynomial. Secondly, we saw how to find the minimal polynomial. So, for a given matrix, if you want to find the minimal polynomial, first find the characteristic polynomial and then consider the all possible factors of the characteristic polynomial. And then start with the factor of the lowest degree and then substitute matrix into each one of them and see that out of these factors, which is the factor with the smallest degree that annihilates the polynomial. So that polynomial is going to be the minimal polynomial actually. So that's really the algorithm for finding the minimal polynomial. Okay? Let me define next another important thing, which is the minimal multiplicity, and then let's talk about these notions. Let's recall the multiplicities that we defined last time. So we defined what we mean by the geometric multiplicity. Okay? Multiplicity of an eigenvalue lambda. So we defined the geometric multiplicity, we denoted it by G lambda as the dimension, okay, of the eigenspace associated with eigenspace of the matrix A associated with lambda. Okay. So and this eigenspace is what actually? So this eigenspace is the dimension of the null space of A minus lambda I actually. So compute the null space of A minus lambda I, that is going to be the geometric multiplicity. So we defined it yesterday. We defined algebraic multiplicity. Okay. What was the definition of algebraic multiplicity? The definition of algebraic multiplicity of an eigenvalue lambda is that what is the power, how many times this factor x minus lambda, okay, appears in the characteristic polynomial actually. So in characteristic polynomials there are going to be other factors depending on the other eigenvalues, but what is the power of, what do you call, the factor, okay, what is the power of the factor x minus lambda in characteristic polynomial? In other words, if this x minus lambda appears d times in the characteristic polynomial, then the algebraic multiplicity of the lambda is going to be d actually. Okay, so the symbol that I'm going to use for algebraic multiplicity is a lambda. Okay, so what is algebraic multiplicity? How many times the factor consisting of lambda appears in characteristic polynomial actually. So if it appears d times, I'm going to say the lambda has algebraic multiplicity d. Now I'm defining another multiplicity, which is the minimal multiplicity. Okay, which is the minimal multiplicity. And the minimal multiplicity is something similar with the characteristic polynomial. In other words, what you are doing with the characteristic polynomial, you do this with the minimal polynomial. I know that the minimal polynomial, in other words, the number of times the factor, minimal polynomial for the, say, eigenvalue lambda, okay, number of times the factor x minus lambda appears in the minimal polynomial. Okay, number of times the lambda appears in the minimal polynomials in, what do you call, the factor of x minus lambda appears in the minimal polynomial is going to be the multiplicity of lambda. Okay, so what is minimal multiplicity? Number of times the factor x minus lambda appears in the minimal polynomial actually. So the minimal multiplicity, if you have such kind of a minimal polynomial for lambda, I'm going to denote it by m lambda is equal to, what do you call, d. Okay, what do you call di? Let's do one example and let's see what are some of, let's do one example for which let's compute, say, minimal polynomial and the characteristic polynomial actually. And not minimal polynomial, but let's compute these multiplicities actually. Okay. Consider a matrix A. Here's an example. Consider a matrix A that has this, that goes like 0, 1, 4. Okay, 7 point. It's the matrices same as the previous one, 1, 4, 4, 0, 2, 1, okay, and 0, 0, 2 actually. And the matrix B is what? 1, 1, 4, 0, 2, 0, and 0, 0, 2. This is what it is. What is the characteristic polynomial of the matrix A? So we just computed it that it is negative x minus 1, x minus 2 square. What was the minimal polynomial? of the matrix A, we computed it to be x minus 1 times x minus 2 square. Okay? What was the characteristic polynomial for the matrix B? We computed it to be minus x minus 1 times x minus 2 square. And what is the characteristic polynomial, and what is the characteristic polynomial of matrix B? It was this. And what was the minimal polynomial for the matrix B? It was x minus 1 times x minus 2. Okay? So in order to find these multiplicities, first you have to compute the characteristic polynomial and minimal polynomial. This tells you that the algebraic multiplicity of eigenvalue 1, the eigenvalue 1 is 1, and the minimal multiplicity of eigenvalue 1 is also 1 actually. Why the correct algebraic multiplicity of the eigenvalue 1 is 1? Because in characteristic polynomial, what is the multiplicity of x minus 1? So it is power 1 actually. And why the minimal multiplicity of the eigenvalue 1 is 1? Because it's in the minimal polynomial, its multiplicity of the factor x minus 1 is power 1. So therefore this must be 1. How about the eigenvalue 2? In other words, what is the algebraic multiplicity of eigenvalue 2? So algebraic multiplicity is number of times the factor x minus 2 appears in 2. So the algebraic multiplicity is 2, and the minimal multiplicity of eigenvalue 2 is also 2 actually. Okay? Of the eigenvalue 2 is also 2. How about this? In this case, the algebraic multiplicity of eigenvalue 1 is 1, and minimal multiplicity is also 1. How about algebraic multiplicity of eigenvalue 2? It's 2. And what is the minimal multiplicity of eigenvalue? 2. Okay, minimal multiplicity of eigenvalue 2, it's equal to 1 actually. It's equal to 1. Okay? So this is that's how you calculate the minimal multiplicity and algebraic multiplicity. We're going to prove an interesting result in our sooner actually, which says that if the algebraic multiplicity and the geometric multiplicity of an eigenvalue are equal, then that matrix must be diagonalizable. So even studying this multiplicity reveals a lot of a structure of diagonalization of a given matrix. So let's compute, for example, the geometric multiplicity. So geometric multiplicity. So in order to compute the geometric multiplicity, we have to compute the null space of the matrix A minus lambda I. So what would be the A minus lambda I? So if I take a vector V from the null space of A minus lambda I, and I try to determine this V, that what is the form of the vector V in the null space of A minus lambda I. So I need to operate A minus lambda I onto this vector V. Okay? And by the way, you may assume that V has 3 components, V1, V2, V3. Okay? Because everything is 3 by 3. So when you're going to compute it and solve, say, maybe I can call V to be X, Y, Z, and solve this system actually. So that since V is from the null space of A minus lambda I, so the A minus lambda I operated onto V should be 0. Now the A minus lambda I matrix operated onto V is minus 1, 4, 0, 0, 1, 0, 0, 0 operated onto X, Y, Z equal to 0, 0, 0 actually. the first equation is going to give you, so it's going to give you minus x plus y plus 4z equal to 0, and the second equation gives you y equal to what do you call this means that z equal to 0, and this means nothing actually. So you get what? So if you substitute z equal to 0 in this equation, you're going to get y equal to x. Hence, the v that has a form x, y, z is of the form x, y is x, so this must be x and z is 0. So in other words, the null space of the matrix A minus lambda I, okay, is basically the span of the vector. What vector? 1, 1, 0. This is the span of the vector actually. Okay? This is the span of the vector B, by the way. Okay. Let's now study the geometric multiplicities of the matrix A and B. So let's first say compute for matrix A, what is the geometric multiplicity of, say, eigenvalue 1 actually. So in order to compute this, I know that this G1 is really the dimension of the A minus lambda, which is 1, dimension of the null space of A minus I. Okay, this is what it is actually. Okay, it is really A minus I. So if I can know this null space, its dimension is going to be the geometric multiplicity of eigenvalue 1. So in order to know the null space of it, let's take, I'm taking for example a vector x, y, z from the null space of A minus I actually. Okay. By the way, all these matrices are 3, so this vector must be, vector with the 3 entries actually. So what I can do now, that I want to find that okay, what are the vectors x, y, z that belong to the null space of A minus I. So in order to find this, you need to apply A minus I onto x, y, z and equate it to 0. Okay? And equate it to 0, or in other words, let me write it in a vectorial form, that you need to find all v such that you get a 0. Now what is A minus I? So if you compute A matrix and subtract, say, identity matrix from it, you're going to get 0, 1, 4, 0, 1, 1, 0, 0, 1, and x, y, z. This is what that you're going to get. And equate it to 0, 0, 0. So when you're going to simplify this, you're going to get, from the first equation, you're going to get y plus 4z equal to 0. From the second equation, you get y plus z equal to 0. And from the third equation, you get z equal to 0. Okay? Z equal to 0. Now, if z equal to 0, what would be y? So this implies that y is also 0. So you substitute it here or here, and from both equations you get y equal to 0. And hence, the vector v, which belongs to the null space of A minus I, has a form x, y, z, but it y is 0 and z is 0 in general. So this is a vector which is kind of span actually. This is a kind of a general form of a vector in the null space of A minus I. So you can say that the eigen